All right, so unfortunately, the recording didn't work for the video on today's lesson, so I'm not going to upload it. However, I will upload this whole document so you've got all of these notes and everything. Or I'll email these to you more so. And I will upload this video that I'm recording now, obviously, because that's how you're watching it. So we got up to, in this titration question here with the burette as the first part, we got up to here. So we just worked out the moles of sodium hydroxide, and we want to use the reaction equation to work out the moles of sulfuric acid. I did actually make a little bit of a mistake earlier on. When we did it in the lesson, I wrote this part the wrong way around, so we'll just start fresh here. So if we look at the reaction equation, we know that the mole ratio of KOH to sulfuric acid, which is H2SO4, is 2 to 1. That means that for every 2 moles of potassium hydroxide, we get 1 mole of sulfuric acid, which means that we get half as much sulfuric acid as we do potassium hydroxide. Therefore, we know that the moles of H2SO4 is equal to half the moles of potassium hydroxide. Therefore, this is going to be equal to half of 0.00400851, that number up there. I'll just highlight that. So that number there. And that's hence equal to, just put that in a calculator, 0.00204 moles. Cool. So hence determine the molar concentration of sulfuric acid. So N equals 0.00204. That is a carrying number that we're going to use in the calculation, so the number from the calculator. The concentration equals question mark, we're not sure of that. The volume, so what was the volume of sulfuric acid? So if we go back up and read the question, we're told that a 20 ml aliquot of sulfuric acid solution was pipeetted into a conical flask and then tied against. Therefore, our volume of acid is 20 ml. So from that, our volume here is going to be 20 ml, which is 0.02 litres. Therefore, concentration, if we just think about our triangles, N equals CV, therefore C equals N over V. However you remember how to do that equation is fine with me, as long as you get it right. You're going to have that 0.00204 ... and that's a carrying number, divided by 0.02, and that's going to be equal to, put that in a calculator, 0.102 moles per litre. State the molar concentration determined above using the appropriate amount of significant figures. So remembering that the appropriate amount of significant figures is using the least given to you. So scrolling back up and looking through our information, this number here is given to 3 significant figures because obviously 2 is non-zero. The 0 at the end is significant because it is after the decimal place with a number to the left of it, and obviously every number in between. So that's the 3. This here is the 3, obviously, because it's 3 non-zero numbers. This one here is the 3 because it's 3 non-zero numbers. Looking for other information given. This is given to 3. This here is given to 2. This is given to 3. Beautiful. So 2 significant figures is the least that we've seen. So I'll say our answer is the two significant figures, and therefore it's going to be an answer of 0.10 moles per litre, the two significant figures. I'm just going to check the solution for that, because there is a reason that I don't believe that's completely correct, but I won't go into it if it says that this is the correct answer. So through part 3. Alright, so the solution here says it's the three significant figures. Now the reason why is that our smallest value, other than that one we found, were all the three significant figures. The only reason that we'll say that this doesn't count is because the volumetric flask we know makes up an exact volume, an exact value, so we'll say that this can be significant to 3, even though there's only 2 here. I think perhaps if I'm marking your test and you said 2 because of this, I would still give it correct, obviously, because I've said that there. But yeah, let's go 0.01 to 3 significant figures is the better answer. And determine the mass concentration. So if we have 0.10215, just that number from the calculator, mole per litre, and we want to go to grams per litre, we know that to go from mole to grams, if we have mole and we want to go to grams, we times by m, and that comes from this triangle. So we'll times by the molar mass. The molar mass of sulfuric acid is going to be, so let's just write this out, 0.10215. The molar mass of sulfuric acid is going to be 2 times 1.008, as that's hydrogen, plus the molar mass of sulfur, which if we just check that, I just need to find it, is 32.06. Plus 4 times the molar mass of oxygen, which is 15.99. Therefore, that is equal to, putting that into a calculator, 9.975 grams per litre. During the titration, the volumetric pipette used to transfer 20 mils of aliquot was only rinsed with distilled water before use. Explain the effects of the calculated concentration of sulfuric acid. So we've got our pipette. Now, obviously, I don't want you to draw things when you're doing the test. I'm just drawing this to help visualize it. We've got our pipette here, and that's got a 20 mil volume. We wash it with distilled water, and that leaves some water residue on there. We then fill it up with our H2SO4, which I'm going to sort of scribble in as blue here. And we go nicely up to that mark from reading eye level, all that jazz. But there's still some distilled water present in here. Well, that means that the H2SO4, if there's some water present in here, it's going to be dilute by the water that was in there as residue. So the H2SO4 is going to be slightly dilute. This means that the concentration of H2SO4 being tested will actually be decreased. Therefore, if the concentration is decreased, in the conical flask that we're titering into, there's going to be less moles of H2SO4 in there, less because of the lower concentration, which means there's going to be a lesser titer value. If the lesser titer value, so I'm going to call it VT, so that's of our base that's being titrated into there. So that's going to be decreased, that's going to be smaller. If N is equal to CV, then the moles of our titer is also going to be decreased, because this V here was decreased. Now we're going to use a mole ratio to work out N. So therefore, the mole of potassium hydroxide is smaller. Therefore, the moles of H2SO4 will be smaller. And as C equals N divided by V, we've made this number here smaller because that's this number here, which is also smaller. If that's smaller, then our concentration is also going to be smaller, or going to be lower than the true concentration. So the calculated concentration is going to be lower than the true concentration. A student wishes to determine the concentration of acetic acid in vinegar bought from a bottle shop, bought from a shop. The student dilutes the sample by taking 25 milliliters of vinegar and makes this up to a total volume of 250 milliliters with distilled water. The student then uses 20 milliliters of this diluted vinegar in a titration with 0.08 molar standard solution of sodium carbonate using phenolphthalein as the indicator. The student obtained the following results. Identify the titer value that would be considered the rough. The rough is normally going to be the first one, but more so it's going to be the one that doesn't, is off, it's not concordant. So this is the rough here, because it differs from the others quite greatly. So we'll say titration 1. Identify the titer values that are considered concordant. So let's just remember, what does concordant mean? It means that they agree with each other. You can think about that as a basic English definition. To concur with something means to agree with it. Otherwise, just think, concordant, the same. So the ones that are concordant, I'm going to say, obviously are 2 and 4. I will say are 2, 3, and 4. Reason being, all of these are within 0.1 milliliters of each other. So we'll say, explain what this term means. Identify the titer values at 2, 3, and 4 because they're concordant. As they agree with each other. Calculate the average titer value for the titration. So we're not going to think about the rough titer, we're only going to use the concordant values. So the average, which I'll say is VAV, or V average, equals 24.4 plus 24.3 plus 24.4 divided by 3. We're not going to use this one here because it's not concordant. We don't agree with it. We're not going to use it. So putting that into a calculator, it gives us an answer of 24.367 milliliters. Very important to remember your units. They're in milliliters here. So obviously it's going to be in milliliters here. You could convert it into liters if you wanted to, but if it doesn't ask you to, just leave it in milliliters, keep it simple. Part 2, so this part here, takes into account significant figures, so I'll do that for you in these calculations. The equation below describes the reaction between acetic acid and sodium hydroxide. So obviously I imagine this is a typo, and this is meant to say sodium carbonate. Between acetic acid, which is that there, and sodium carbonate, which is that there. Maybe I'll highlight those. Calculate the number of moles of sodium carbonate in the average titer. Oh, where's the information? Maybe we'll skip this question because from the look of it, we're not... Oh, sorry, perhaps it was this question up here. All right, so yeah, the information for this question comes from the page above, up here. So, what's being asked? Calculate the number of moles of sodium carbonate in the average titer. So N equals question mark, concentration equals, let's go and have a look. The student dilute, so we're looking in a titration with 0.080, oops, let's not use that. 0.008 standard solution of sodium carbonate. So therefore, we're going to have a concentration of 0.080 mole per litre. Just going to highlight that in green so you know where it comes from. And the volume so just to give an idea of this, the student takes 20 milliliter samples of vinegar and they dilute it, they titrate it against the sodium carbonate. So the sodium carbonate is in the burette, so these volumes are what's in the burette. So we're going to use that average titer of 24.367 moles, which is 0.024367 litres. This value here was actually 0.0243666666, so we're going to use that in the calculations. I'll just highlight these just so everyone knows where they came from. Cool. So N equals CV equals 0.08 times 24.36666 is equal to 1.949 moles. Alright, so next, using the reaction equation, calculate the number of moles of diluted acetic acid in the 20 ml aliquot. So our mole ratio between sodium carbonate and acetic acid is 2 to 1, which means for every 1 mole of sodium carbonate, we're going to have 2 moles of acetic acid. Therefore, we have twice the amount. So, NaCH acetic acid, as we said, we get twice the amount of sodium carbonate, so we're going to times that number by 2. And that means just times the previous number by 2 is going to give you to 0.00389 moles. I'm just going to very quickly just check the answers and see how we're going just to make sure that that number's right, just because I am just doing these on the fly at the moment. Where are we up to? 0.019. Yeah, cool. So just make sure I'm correct. Now, something important that I forgot to keep track of, we are looking at significant figures for this part. So for this one here, in our calculation, our concentration was given to 2 significant figures, and our volume was given to 3 significant figures. Therefore, our final answer is the 2 significant figures. So that's going to be 0.0019. We don't round that 9 up to that 4 up to a 5, then that 9 up to a 2.0 or 20, because 49 is closer to 19 than it is to 20 in this case. Alrighty, and then this here is also going to be the 2 significant figures, because we only had 2 significant figures in this starting answer here, regardless of the fact that we had 3 here. So this number is also the 2 significant figures. Oops, oh gosh, I don't know where I clicked. Cool. Hence determine the concentration of the diluted acetic acid. So if N equals CV, then C equals N divided by V, or you can use your triangles. That's going to be equal to a point. Now we're going to use that carrying number from the calculator, not the rounded number. Divided by the volume. The volume of the acetic acid, we're told, was 20 mils, because the student uses 20 mils of diluted vinegar to tighten with. So that is therefore equal to 0.02. I might just give those a highlight just so we can remember where those values are from. So then plug that in the calculator, make sure to use your non-rounded answer, which will give you a concentration of 0.1949 moles per litre. Again, only working at 2 significant figures, which will be a concentration of 0.19 mole per litre, because that'll round down to 19, not up to 20. Alright, so determine the concentration of undiluted acetic acid. So from my information here, which I've just copied and pasted down here, our starting concentration, we don't know. That's what we're trying to find. Our starting volume was 25 millilitres, so 0.025, as we removed 25 millilitres. Our finishing concentration, we found that our sample had a concentration of this up there. So we'll use the unrounded number for that calculation. And then our finishing volume was 250 millilitres, because that's what it was made up to when it was diluted. So 0.025. Therefore, if C1 V1 equals C2 V2, C1 equals C2 V2 divided by V1. Sorry, I just made a little mistake. That V2 there was 0.25, not 0.025. Cool, so that's 0.25 litres. So C2 times V2, which is 0.25, divided by 0.025 equals 1.949 moles per litre, and that equals 1.9 moles per litre to 2 significant figures. My answers do vary slightly differently to the solutions given. Something I noticed, as can be shown, that is just because at some point I've rounded either more or less than what the answers have, and that's just made it slightly different. If you're going to get it that close, I'll most probably mark you correct in the test. Also up here, I just realised as well that this answer here of the average titer should have been done to two significant figures, which would just be 24 millilitres. Cool. Alrighty. I'll try to smash this last bit. Precision and accuracy of the titer values obtained during a titration are affected by a variety of errors. Identify the type of error that affects precision. So a random error affects precision. Identify the type of error that affects accuracy is a systematic error. If we think about our dartboard analogy, precision, all in the same spot. A random error is going to affect one of these things separately, and that's going to change precision. If we're affecting accuracy, we're going to move, a systematic error is going to move all of those away from the true value that's in the middle. Endpoints are often judged in titrations by a colour change. State and explain whether this method of endpoint determination decreases or increases precision or accuracy. The method being observing a colour change. I might just see if there's any information I'm missing. Just trying to look at what they said for that answer, because I think there's a few different things. Okay, yeah, sweet. So if you're judging endpoint by colour change, you're literally just a human looking at the colour change. Obviously, when you're going to pick that colour change, your eyes, there's that human error that comes into play with it. So therefore, you're not going to be able to say that the colour change occurred perfectly at each time. So human error is going to cause each endpoint to be determined differently. So also each endpoint is different. I'm just going to shorthand this and skip some words out. And this leads to a random error, which will decrease precision. Cool. State and explain the effect of the titer values obtained in the titration when a solution is left to stand in a burette for an extended period of time. So I'll just explain this to you, I won't write it out. If we've got a burette, my badly drawn burette, we've got solution in it. It starts off with being homogeneous because it's all nicely mixed through. If it's let it sit for an extended period of time, all of these ions that are in here are no longer going to be homogeneous. The heavier ones are going to sink to the bottom, like so, and there'll be less up here. So, state and explain the effect on titer values. Your first titer value is going to be much smaller because all of these moles and molecules are going to come straight through in that first titer, and then your remaining titer values are going to be a lot larger because less moles are coming through in the remaining titrations. Last question, identify and explain one error that would cause a decrease in the accuracy of the titer values from the titration. So how can we decrease accuracy? So one random error, and we could say error of parallax, for example. And if you look from a different, not from the eye level each time, if you look from a different position each time, you're going to get different readings. We could also say misjudging the endpoint. There's heaps. Error of parallax, misjudging the endpoint. Just look at some of the solutions there. Oh, sorry, hold up. What have I done? Decrease the accuracy. Sorry, they should be systematic errors. So systematic errors could be making a, incorrect stock solution concentration at the start would cause a systematic error because then you're tying against a wrong stock solution concentration. Another one could be not weighing correct mass when making a stock solution. Again, it's kind of like that. Just various systematic errors. Cool, I'm going to leave it there because I am super tired from making this. Any questions, just send me an email. Cheers.